Swayam Prabha. Digital India. Educated India.
Okay, look at this set. I have one. This is a constant function, cosine square t, sine square t. These are three continuous functions, yeah, from R to R. Let us see whether they are linearly dependent or independent. Yeah. So you all know this relation, cosine square t plus sine square t minus 1 equal to 0. So here is a linear combination of these three functions. It's a non-trivial linear combination because the coefficients are 1, 1, minus 1. Yeah. We have a non-trivial linear combination of these three functions which produces the zero function. This left hand side is zero function because of the trigonometric identity. So these three functions are linearly dependent. Okay, yeah. Now let me produce an infinite set of linearly independent set. Infinite linearly independent set. Okay, we will see later. You cannot do that in Rn. Infinite sets which are like linearly, and after that it involves exponential function. Alpha 1 is less than alpha. I could take any n. Just look at the space of all continuous functions. This is my vector space. Okay, in this vector space, I want to produce infinite set of linearly independent functions. Okay? Here it is. So let's look at e to the power alpha to the power alpha 2x, e to the alpha n. Yeah, e2x, e3x, and so on. Look at all these continuous functions. Okay, and truncate e alpha x. So these are n continuous functions. In fact, they are much more than continuous. They are infinitely often differentiable. So that this is a linearly independent set. I can take n real alpha to power alpha nx, and let us show that they are linear. So to show that these are linearly independent, I must show that no linear combination of non-trivial linear combination of them produces the zero function. So take a linear combination, but we will apply induction. So take n equal to 1. When we have n equal to 1, I have e to the power alpha 1x, and suppose that beta times e to the power alpha nx equal to 0. But we know that this exponential function is never 0. Yeah. So I can divide by e to the power alpha 1x for any x and get beta equal to 0. So this actually is true in general. A non-zero vector in any vector space is linearly independent. But in this case, our non-zero vector is this exponential function, and we have shown that it is linearly independent by itself. So this statement that the set E alpha 1x, E alpha 2x, E alpha nx is linearly independent has been proved for n equal to 1. Now I assume this fact for any n minus 1. Assume the assertion is true for n minus 1, and we will prove it for n. So take this n exponential functions and take this linear combination where coefficients are beta 1, beta n, and this is produces the zero function. Then I want to show that each beta I is 0 for all I. Yeah. So if I have this linear combination of E alpha 1x, E alpha nx, producing the zero function, I want to prove that all the betas are equal to 0. Somehow we have to reduce this equation to an equation which has n minus 1 function so that we can use our induction hypothesis. Okay. So, but now use this fact that alpha n is bigger than alpha 1, alpha 2, alpha n minus 1. So this equation I can multiply. Okay, I can multiply this equation by e to I can divide this equation or multiply this equation by e to the power minus alpha nx. This is also a function. See, if this is the zero function, I can multiply by this function on the both the sides. I still get this zero function, but then I get this relation. And this last function, okay, alpha n minus alpha n, that is equal to 1. So we just get e beta 1 e to the power alpha 1 minus alpha n x and so on. And the last one is beta n. Okay, the last one is beta n. But now I can let x approach to infinity. This is a function of x. Yeah, it's a continuous function of x which produces this zero function. So if I take x approaching to infinity on both the sides, I should get this zero function. But when I let x approach to infinity, then this is a negative real number, and this is zero. Okay, so when x is approaching to infinity, this function is mapping to zero. Okay, so in this relation, I will get only beta n. When I let x approach to infinity, the limit of the left hand side function is just beta n. The limit of right hand function is 0, and therefore beta n is 0. So I can put beta n equal to 0 here. Yeah. So I started with this linear combination of n exponential functions by dividing by e to the power alpha n x, and then taking the limit. I approve that beta n equal to 0, substitute beta n equal to 0, then I get a relation between n minus 1 exponential function. But by induction hypothesis, then if a linear combination of n minus 1 exponential function is 0, then those are linearly independent. So all the betas are 0. Once all the betas are 0, I go back and substitute into this. I get beta n e to the power alpha n x equal to 0, and that forces beta n equal to 0. Okay. Yeah. So therefore, I have proved that if I take any distinct real numbers, alpha 1, alpha 2, alpha n, then construct the exponential functions e to the power alpha n x, e to the power alpha 2x, etc., then these distinct exponential functions are linearly independent. So the vector space of all continuous functions has arbitrarily large linearly independent set of functions. Yeah, this is how a vector space of continuous function is different from a n-dimensional Euclidean space Rn. We will see that n-dimensional Euclidean space Rn cannot have infinitely many linearly independent vectors, but the function space of continuous functions can have infinitely many linearly independent functions. Okay, yeah. So let's now look at the vector space of all polynomials. No condition on the degree. Just take all polynomials, real polynomials. Coefficients are real numbers. We could also consider polynomials where the coefficients are complex numbers. Yeah, same statement will hold. So in this, every polynomial is actually a real linear combination. Real polynomial is a real linear combination of 1 t square, etc. These are monomials. So every polynomial is a unique linear combination of these monomials, 1 beta. So in this space, let us see that if I take these monomials t to the n1, t to the n2, t to the nr, where the powers are distinct, then they are linearly independent. Okay. So take a linear combination which produces 0. I want to prove that alpha 1 is 0, alpha 2 is 0, alpha r is 0. And this earlier we multiplied by e to the power minus alpha n x and took the limit. But now we can differentiate. Okay, we can differentiate. So if I differentiate, say nr times, then these things will go to 0 if I differentiate nr times, and this alpha r will be multiplied by some number, and that function will only survive, and that will say alpha r is 0. So differentiate this relation on both sides n1 times, I will get, and then put t equal to 0, I will get alpha 1 equal to 0, and continue this way. Okay. Or you can differentiate nr times, and then you will get alpha r equal to 0. Then differentiate nr minus 1 times, and substitute that will give me other coefficients to be 0. So distinct monomials, t to the n1, t to the n2, t to the nr, these distinct monomials are linearly independent in the vector space of all real polynomials. So the vector space of all real polynomials and vector space of all continuous functions, they have this common property that there is no bound on the size of linearly independent sets. There is no bound. Okay? And so they differ from ordinary Euclidean space with this property that in ordinary Euclidean space you cannot have infinite set of linearly independent vectors. There will be a bound. We want to show that. Okay, so that is done by introducing what is called basis and dimension. Vector space comprised a linear span of several sets. Okay, we have seen that several sets of. So if my vector space is linear span of say E1 and E1 plus E2, then also linear span of E1, E2, E2, E1 plus E2, or 2E1. You can always okay, linear span of S is equal to V, and T is a subset of V. Then linear span of S union T is also V. Okay, so I can enlarge a given set and still get the same vector space. But in practice, we want to take smallest set whose linear span is a given space. Yeah. So vector space can be realized sizes. Yeah. Study properties of smallest sets whose linear span is a given value. Yeah. So let me first express in words what is a basis. So a subset is a basis of a vector space if elements of S are linearly independent and the vector space is linear span of that. It's a fundamental. A subset of a vector space is called a basis of a vector space. Elements are linearly independent. That means whenever of elements of S produces a zero vector, then it's a trivial linear combination. And the whole space is linear span of the given set. Yeah? Whole space is linear span of the given. Vector space is linear span of a finite set. We will say the vector space is finite dimensional. Otherwise, is called infinite dimension. So you can expect that the vector space of all real polynomials will be infinite dimension. Because if I take finitely many polynomials, they have bounded degree. There's a upper bound on the degree. So I can't get polynomials of higher degree as linear combinations of polynomials of lower degree. So the vector space of all real polynomials is obviously infinite dimension. But a finite set of polynomials, if I take linear combinations, then there is a upper bound on the linear combinations of a finite set of polynomials. So the real vector space of all real polynomials is actually infinite dimension. Okay. So take a basis of a finite dimensional vector space. Suppose I have a basis of finite dimensional vector space. That means a finite set. That is the definition of finite vector space, that there is a finite set which is linearly independent, whose linear span is the whole. Yeah? Just like E1 and E2, if I take in R2, their linear span is the whole space, and E1 and E2 are linearly independent. Similarly, I showed you that the n basic column vectors E1, E2, En, they are linearly independent in Rn. So Rn is linear span of E1, E2, En. E1 and E2, En are linearly independent. So E1 up to En is a basis of the given vector space. So if I have a finite dimensional vector space and V1 up to Vn is a basis, then every vector can be uniquely expressed. This is important. Every vector is a unique linear combination of elements of the basis. These A1, A2, An, they are uniquely determined. So if I have a basis, that means it's a linearly independent set whose linear span is the whole space, then every vector in V is unique linear combination of V1 up to En. So look at this situation Rn. Rn is linear span of E1, the standard basic column vectors. and every vector v, suppose v is the vector v1 v2 with components vn, then v is equal to v1 e1 v2 e2 plus vn en, and these vi's are obviously uniquely determined. So every vector in Rn is a unique linear combination of e1 e2 en. But you see, I showed you R2 is linear combination of e1 and e1 plus e2 also. So every vector can be uniquely expressed as alpha 1 e1 plus alpha 2 e1 plus e2. You can easily check that this can be done. Okay. So whenever I have a basis, then every vector in that vector space is a unique linear combination. So there is a question: is a unique linear combination, or even you do not even? But you see, yeah. Okay. Yeah. Okay. So let us prove this. Let us prove this fact. We show that all bases of a finite dimensional vector space have same cardinality. Yeah? They contain the same number of elements. Okay. All bases of a finite dimensional vector space have same cardinality. They contain the same number of elements. So this proposition I am leaving you as an exercise. It's a easily proved fact that every vector can be uniquely expressed as a linear combination of basis vectors. Yeah. So let's now we want to prove that any two bases of a finite dimensional vector space have same number of elements, and that will lead to the definition of dimension of a vector space. Okay. So take a set v1 v2 vk. Suppose it's a subset of a vector space. Then the linear span of S consists of infinitely many vectors. If I take a real vector space, it will consist of infinitely many vectors. Even linear span of one non-zero vector has infinitely many vectors. So if I take a non-zero vector, say in the plane, and take its linear span, it considers all vectors sitting on that line which is containing the vector. So linear span of even a one non-zero vector has infinitely many vectors. So the linear span of these k non-zero vectors, yeah, this has infinitely many vectors. But in this linear span, if I take k plus 1 vectors, they will be always linearly dependent. Yeah. Okay. So my linear span is linear span of k vectors, and I'm saying that any k plus 1 vectors in this linear span will be linearly dependent. So if a vector space is linear span of k vectors, then its dimension cannot exceed k. That is a consequence of this fact. Yeah, because any k plus 1 elements will be linearly dependent. If the dimension exceeded k, then we will have more than k vectors which are linearly independent. But this lemma says that if I take a vector space with a linear span of k vectors, then any k plus 1 vectors in the linear span are linearly dependent. Okay, this is very crucial. This will immediately imply that any two bases of a finite dimensional vector space have same number of elements, and that number is called the dimension. Okay, so we are not appealing to any geometric intuition here. So our geometric intuition fails beyond dimension 3. We can't imagine 4-dimensional, 5-dimensional spaces. So we have to come out with a definition which can be, which is efficient, which is algebraic, and it can be tested. Okay, the criterion can be tested. We can find out the dimension simply by writing some programs. Okay, so this lemma will imply that dimension of vector space is a well-defined notion. Okay, so let's prove this, that any k plus 1 elements in linear span of k vectors are linearly dependent. Okay, so let us look at the set of k plus 1 vectors. We are saying any k plus 1 vectors. So I take k plus 1 vectors. Yeah, I take k plus 1 vectors in the linear span of S, and I want to show that these k plus 1 vectors are linearly dependent. That means I must produce a non-trivial linear combination. Yeah, I have to produce a non-trivial linear combination, alpha 1 u1 plus alpha k plus 1 uk plus 1 equal to 0. Somehow I have to produce a non-trivial linear combination of u1, u2, uk plus 1, which produces a 0 vector, assuming that linear span of these k vectors is this space. Okay. Yeah. So let us write down. So each one of these vectors, what is the information we have? Each one of these vectors is a linear span of these k vectors. So write down this equation: ui equal to summation aij vj, where j equal to 1 up to k. So this ui is in the linear span of v1 up to vk. Ui is a linear combination of v1 up to vk. I write the coefficients as aij. I do it for every r. Okay, there are k plus 1 vectors which are linear combination of these k vectors v1 up to vk. Yeah, so that means ui's can have these formulas. They are linear combination. Okay, now so this gives rise to a k plus 1 by k matrix, because I have k plus 1 vectors which are linear combination of k vectors. So in those relations, the coefficients aij, okay, coefficients aij, I is varying from 1 up to k plus 1, but j is varying from 1 up to k. So if I collect all those coefficients in those linear combinations, I get a k plus 1 by k matrix. Yeah. So this k plus 1 by k matrix, it has more rows than columns. Yeah. It's a tall matrix. There are more rows than the columns. Yeah, there are more rows than the columns. There are k plus 1 rows and there are k columns. K plus 1 by k matrix. Then this is my matrix A. Then I want to see that xa is 0. There is a non-trivial x which is non-zero. Okay, let us see that. Why I can find, if I have a tall matrix, if I have a tall matrix, there is a non-trivial x. So instead I look at A transpose, k plus 1 matrix. So there are k rows and k plus 1 columns at bottom of A y. But this matrix A transpose has k rows and k plus 1 columns. So it's a fat matrix. It's a fat matrix. There are k rows, lot more columns. And I have this homogeneous system of linear equations. So when I convert this A transpose into its row echelon form of A transpose, it will have k rows and k plus 1 columns, and therefore at least one column vector, there will be one, when you look at the pivots, number of pivots cannot exceed k, because there are k. So there is at least one non-pivotal column. Now if you have a homogeneous booleans which give rise to one non-pivotal column in the row echelon form, then the given homogeneous system of linear equation has a non-trivial solution. Yeah, this we have seen before. The number of free variables is equal to number of non-pivotal columns in the row echelon. But if I have k by k plus 1 matrix, then there will be at least one non-pivotal column, and therefore A transpose A transpose Y, that has a non-trivial solution. Once it has a non-trivial solution, then I can just look at A transpose and just look at A trans and A transpose, that is equal to 0. So this is my vector x. This is my vector x, or we can call it vector c, so that c equal to 0. So if A is a tall matrix, which means there are more rows than then there is a row vector c, so that c is 0. Okay, that's what I'm saying here, that this k plus 1 by k matrix, which came from the coefficients. When I write these k plus 1 vectors as linear combination of k vectors, then I get this k plus 1 by k matrix. So this discussion says that there is a vector c, row vector c, so that c equal to 0. That means if I display the components of bound by K matrix. So this has K plus 1 components, C1, C2, Ck plus 1. Yeah. Then I multiply Ca is a row vector, and in the components of the row vector are these: Ci equal to 1 up to K plus 1 equal to 0. So this I get this linear relation among Aij for every j, and now go and look at, say, C is this vector, Ca equal to 0. I look at this linear combination Ci ui. Okay, but ui is this sigma Aij Vj, and now I can interchange these two sum and Ci Aij Vj. This relation among V1 and K. So that shows U2 UK plus 1, this linear combination is 0. Not all the CIs are 0 because CIs are components of this non-zero vector. So therefore, these K plus 1 vectors are linearly dependent. On this is a very important fact that linear K vectors